Welcome to Exam Race. Today we would be discussing a very important topic, which is the simple harmonic motion, also known as SHM, and oscillatory motion. So oscillatory motion, there are of several kinds. One of them and the most important one is the SHM. So before we move on to the SHM, let us understand a very simple concept, which is the periodic motion. Now the periodic motion is a motion which repeats after certain amount of time, after a fixed amount of time. So a very simple example of a periodic motion is the Earth rotating about its polar axis. So about the polar axis, we know that the Earth rotates round and it completes one such rotation in 24 hours. This 24 hours is known as the time period of this periodic motion, and the motion is periodic because it is repeating after certain fixed amount of time, and the time is known as the time period of the motion, and in the case of the rotation of Earth it is 24 hours. So there are several kinds of periodic motion. Several examples are given here. One of the most important types of periodic motion which repeats after certain amount of time, after certain interval of time, is the SHM. So SHM is not only a periodic motion, but it has more other special properties as well. So one of the most important thing which is very special about SHM is the restoring force. Now this restoring force, let us understand what this restoring force is by using a simple example of this mass which is attached to a spring. So this is the example that we will be using to understand our SHM. So here is a mass which is attached to this spring, and the surface here, it has a property. The property is that it is frictionless. Okay, so we will simplify our assumptions so that we can understand the equations better. So this surface is frictionless. Okay, so from our experience and from our understanding of the Hooke's law, which we have already studied, we know that there is a neutral position for this spring. So what is the neutral position? So if you leave the spring as is on the surface, whatever is this natural position, whatever comes about is the neutral position of the spring. So this is the spring in the neutral position, and when the spring is in this position, it is not causing, it is not putting any force on this mass m. So in this neutral position, the spring exerts no force on this mass m. This position is known as the x equal to 0. So this is just a convention, for our understanding, for the sake of simplicity. We have just said that this neutral position where the force of the spring is 0, it is not exerting any force. We have just said that this position is x equal to 0. Now if I pull the spring, if I stretch this spring, and let's say that I stretch it by an amount x, then we know that there would be a restoring force which would be exerted by the spring. It will try to pull the block back. Okay, it will again try to pull the block back, and this Fs is known as the restoring force. Now one of the most important thing about this restoring force which is exerted in the case of spring is that from the Hooke's law we know that it is proportional to the amount of stretching of the spring. So the more I stretch the spring from its neutral position, the more would be this restoring force. Okay, so this restoring force Fs would always try to bring back the spring towards the neutral position, and this Fs is directly proportional to the amount of stretching, or to the amount of this displacement x. The more this displacement, the greater is this force, and that comes by the Hooke's law. Okay, and we understand the limitations of Hooke's law, that it is only in this elastic region that this would apply. Okay, so all of those things we are saying are valid in this case. So whenever there is a motion due to this restoring force, which is proportional to the displacement. Whenever this in the case of motion, there is this restoring force which is proportional to the displacement from the mean position, from the x equal to 0 position. Whenever such a force is present, the body would undergo a SHM. Okay, it will always undergo a simple harmonic motion. So the same thing applies to a pendulum. There is a restoring force which is always present even in the case of pendulum, which is trying to bring it back to its neutral, the perfectly vertical position. Okay, the restoring force is present there, and that is why the pendulum also undergoes the SHM. So that is the basic requirement of an SHM. And whenever we have SHM, the SHM is always periodic. So in the case of spring, what would happen? In the case of this spring mass, what would happen? The body we would stretch the spring a little bit and then we will leave it. So what would happen? So we stretch the spring and then we leave it. So it starts from this position right here, x right here. Okay, it goes to the neutral position, but of course when it reaches the neutral position, although there is no force at this point, but it already has momentum, it already has certain velocity, and because the friction, the surface is frictionless, the body would overshoot this position and then it would come to this position. It would traverse a distance of x in this direction. From the neutral position, it would come to this displacement. Okay, so this we'll call it minus x because it is towards the left side of the x equal to 0. So the body then comes to minus x, and from this minus x it will again go back to neutral position, and then it will come to this location, go back to the A position again, and this way it would continue to vibrate, it will continue to oscillate. Okay, and this SHM is what we would be now understanding. The equation of this SHM is what we would be trying to derive next. Okay, so as we have seen that this is the basic equation of a restoring force in the case of an SHM. And what this tells us, it tells us that the restoring force is always directed opposite to that of the displacement. So if my displacement is in plus x direction, okay, so this is x equal to 0, this is plus side and this is the minus side if you consider the coordinate system. Okay, so my restoring force is always directed opposite to the direction of displacement. My displacement is in this direction, then my restoring force, the force which is exerted by the spring to bring back the mass, this mass, bring it back to the equilibrium position. So this is the equilibrium position. So with this basic equation, now let us replace this Fs. We know that this force is equal to mass into acceleration. So I can write it like this. And this, of course, then I can write it as acceleration is equal to minus k by m into x. And this is another important equation for our SHM. And sometimes people say that if my acceleration, instead of defining the restoring in terms of restoring force, sometimes people define it in terms of this acceleration as well. So if my acceleration is such that it is always opposite to displacement and proportional to